Well, maybe she only wants 2 points.
All right, we ready? Yes. So the second derivative, what do you know about it? You tell me. It's the derivative of the derivative? Sure. Is that all we know about it?
I know
You know the simple things. What is it like?
y, and then it's like Roman numeral
2. Roman numeral 2 for 2, so like 2 ticks, so like y double prime. Sure, absolutely. How about its applications in motion? So like position, velocity.
acceleration.
Our second derivative is the acceleration of our position. What does it mean to be accelerating? It's the rate at which you're changing speed. So if like your speed is increasing or your speed is decreasing, it's like you're slowing down or you're speeding up, means you are accelerating. And that all deals with the second derivative. All right, y'all. We're going to keep talking about the relationships of your f of x function, your derivative function, and your second derivative function. And we're going to relate concavity with our second derivative, which we've kind of touched on already, I think. And then we're going to talk about velocity and acceleration. Woohoo. Okay, class. In this box are 4 different graphs. Which are concave up and which are concave down? How do you know if something is concave up?
If you fill it with water.
If you can fill it with cereal, or did you say water, Megan? If it's like a bowl that's facing up and you can fill it with cereal or water or both, then it's concave up. What if it's concave down?
If you pour cereal on it, it will fall off the side.
Sure. If you pour cereal on it, it'll just fall off. The bowl is upside down. Okay, sure. So concave up. Concave up, and then the bottom 2 are concave down. Okay, y'all. Now tell me. I'm actually going to write this as a side note over here. If your function f of x is increasing, what does that tell us about the derivative? It's positive. So if f of x is increasing, then our derivative, f prime of x, is positive, so I'm going to write greater than 0. Okay, so which of these 4 graphs are increasing? Which of them have derivatives that are larger than 0? I have a vote for the right 2.
Yes.
A bunch of people second that. All right. So can I just title this column? This is going to be when our derivative is larger than 0. That's for the whole column. That makes sense. And then how about if your function is decreasing? What does that tell us about the derivative? That it's negative. So that'll be our other column because both of those graphs are decreasing. They're going down. If x is less than 0. Okay, y'all. And now our kind of new concept for today is if your graph is concave up, that means your second derivative is positive. So in our rows, our 2 concave up functions, this means that our second derivative function is positive. It's larger than 0. our functions that are concave down, that means the second derivative is going to be negative. Okay, y'all. On the side, another way you can think about this second derivative and its applications are if your derivative is increasing, so that means if your derivative is increasing, that means you're like getting faster. What does that tell us about our second derivative then? It's the same pattern. This tells us that our second derivative is positive. It was just a warm up, so you don't need it.
Done.
How much if I make it?
Oh,
Hey, give TJ
Did we?
Extra credit points if he takes it.
can we finish this chart and then we'll go back to that?
Shoot.
Okay. Whew. Okay, y'all. What else can you tell me about the graphs and how they relate to each other? What if your derivative is 0 at a single point? What does that mean? At a point like x equals c, something. What do we know about the original function f of x if our derivative is 0 at a point? It's a peak or a valley, or maybe it's an inflection point of some sort as well. Have we talked much about what inflection point means?
Like that.
Yeah, okay. So it was something that looks like this,
The in between.
and it's in between.
And it switches
What switches?
from
This way to this way.
Mm-hmm. From the left up until the point, we concave up or concave down?
Up.
Concave up. And then how about to the right of this point?
Concave down.
Concave down. Inflection points are the change in concavity. So I'll write that down too. Are you out of room?
Almost.
I'm like halfway through.
Okay. So this will be the last thing we'll write. Inflection point. This means a switch in, or switch with, how do we want to say this?
Change in direction.
It's change in concavity though. Does that make sense to you if I say a change in concavity? That makes sense? Okay. All right. So an inflection point is a change in concavity. And one last fun point about inflection points, this is when your second derivative equals 0. Do you know why? No. We don't see that.
No.
No.
So,
Okay, if your function, or here, I'll just go to this blank page. All right. Let's take a look at something that switches concavity. So like our cubic function right here. Here's a point of inflection, right? All right, if this is our position function, let's graph the derivative. I'll draw, ooh. Can you graph the derivative? What's the slope at this point? This is kind of a bad one. We're gonna go with it. What's the slope at that point? 0-ish. So that means we definitely go through the origin on our derivative graph. You see how this is all decreasing, this graph? What does that tell us about our derivative? It's all below the x-axis. And we start with a steep slope, we go to 0, and then we go back down, right? So our slope decreases and then gets faster again. Does that make sense? So we just created a peak at this point, right? So what's the derivative of the derivative at this inflection point at 0 now? What's the slope of this point on our derivative graph? 0. And that's always the case for any inflection point that you have. Your second derivative will be 0 at that point. Does that kind of make sense? Yeah? Okay. And do we have any questions about this right now? Feel okay? Okay, is that it for this page? No. All right, for the functions below, determine. Oh, yeah. Okay. Your teacher can't remember what's going on. Okay, as our warm-up that I forgot about, what's the derivative of 6x squared minus 4x plus 1?
12x minus 4.
12x minus 4. Did you use the formal definition of a derivative? Using limits?
The big long equation thing? Heck to the no.
Heck to the no. You probably used the power rule, right?
Yes, ma'am.
How'd you do number 2?
times it and then did it.
So we distributed and then used the power rule. Did anybody do anything different?
I used the that one's f of x, and that one's g of x, and then you take the derivative.
Yeah, also did that.
Yeah, same.
Okay, so some of us distributed, some of us just used the product rule. Either way, what do you get?
6x plus 3.
I've got 9x squared plus 6x minus 3.
Yeah.
Shoot, I don't know.
Yeah, that's what I got.
This?
No, I got minus 3.
Minus 3 at the end?
I got,
Oh,
yeah,
I got that.
9x squared plus 8x minus 3.
8x?
Yes.
Yeah, what did we all do?
Ooh, maybe we should do this together quick.
Didn't you get what I got?
Yeah.
All right, y'all. I'll do it using the product rule.
Oh,
So-
I know I did this wrong.
We take the first one times the derivative of the second one, right? So x squared minus 1. What's the derivative of 3x plus 4? 3. Are you okay if I just put the 3 out front here? All right, plus our second function times the derivative of the first function. What's the derivative of x squared minus 1? 2x. Okay, and then I guess if you simplify, so this is 3x squared minus 3 plus 6x squared plus 8x.
Plus 8x.
That's what 2x times 4 is.
Oh, that's right.
Yes.
Ah, gotcha. So this is 3x squared. No, it's not. That's a 9x squared. Plus 8x minus 3.
Yeah, I still think we did.
Still think what you think distributing first was easier?
Yes.
Maybe.
I only wrote 2 lines.
I just forgot how to multiply.
Also,
So,
sorry. We also
Sometimes the
made me worry that I did this all wrong. I was like,
Yeah.
All right, we're okay. We ready to move on now that we. Goodness. I guess a brain break. Kind of using calculus to take a break from calculus, right, y'all? Okay, for the functions below, determine where our second derivatives are positive and where they are negative. How do Okay, y'all, come on.
Get a big boy.
How do we know where a second derivative is positive, class? Concave up. And how do you know where it's negative? Concave down. Take a look at this first graph. Concave up, concave down. Do we switch? Is it both somewhere? The whole time? Yeah. Yeah, it's concave down the whole time, right? So this first one is concave down. This means for all x on the graph, what's our second derivative? Positive or negative? Negative. How about our second function? It's all concave up. So what does that mean about our second derivative? Our second derivative is positive. This one is both concave up and concave down. Okay, when does it switch between the two? Where's the inflection point? At 0, yes. Very good. So at this point is when we switch from being from the left. Is this concave up or concave down? Can I write CC for concave? Concave down, and then we switch to being concave up. And this point is called the inflection point. So how would I describe when our second derivative is positive and negative?
F of x is, well, the second derivative of x is positive, like, it's bigger than 0.
When x is greater than 0,
Yeah.
that's when it's positive. That's when our second derivative is positive.
Then vice versa.
Right, because when x is larger than 0, that's to the right of 0, or concave up, which means our second derivative is larger than 0. And then when x is less than 0, so that means to the left of that inflection point, what does that tell us about our second derivative, y'all? Say it louder. It's less than 0. All right, what questions do we have? If you feel good, then go ahead and flip the page. We'll keep going.
Oh, no.
Why do we say, oh no?
Because there's cars.
Yeah. Acceleration's kind of a tricky topic to understand conceptually. It's nice to understand if you're just talking about concave up and concave down, but in terms of motion, it gets a little goofy because it takes into account your original direction plus your speed to determine if you're accelerating. Okay, let me back up. What is acceleration? Let's get a definition first. Can you tell me?
How fast you go fast.
How fast you go fast. I actually don't mind that. So it's the rate you're changing speed. Okay. Can I change the word speed to velocity? So let's say that acceleration is the rate of change of the velocity. I have a question for you. If you're driving in a car and you're going 55 miles an hour the whole time, you're on cruise, what's your acceleration? 0. You're not going faster or slowing down. You're staying at a constant velocity, therefore your acceleration is 0. Okay. Cool. Is there anything we wanted to say about acceleration? Is there anything else you know about acceleration?
Do it every day in my car.
We do it every day in our cars. It just means that we either speed up or slow down. Okay. How about its relation to a position function, s of t? How does the velocity function relate to our function s of t, our position function? How would you get to, how would you calculate a velocity function given a position function? How does velocity relate to position? Your movement. Okay. So if I write it, you're gonna know what I'm asking for here. I'm fishing.
I just don't understand what you're asking.
Is it like one of those like things that goes up and then goes down?
Yeah, maybe we've done stuff like that before.
Your rate of change.
It's your rate of change, right?
Yeah.
And what concept do we know means rate of change at a single point? So your velocity is just the derivative of your position function.
Oh, I knew that.
Right, okay, I know you know. And your acceleration function, how does that relate to, let's do position first, your s of t function. It's the second derivative of your position function, and which is also equal to, how does that relate to velocity? It's the derivative of the velocity function as well. Okay. And just a side note, if you see the word velocity or acceleration and there's not an average before it, so you're not finding the average velocity, you assume for it to be instantaneous, so you assume that you use derivatives to find it. Cool? Okay. And last example, and then that's it. All right. A particle is moving on a straight line. So it's like if I was moving just back and forth across this room on a straight line, it's me, I'm a particle. Okay, to the right of a fixed point is given by the graph below. Let's estimate the following. Let's first understand what this graph means. And when we're moving right, when we're moving left, when do we switch direction? What does this position graph mean?
When the graph is increasing, you're moving right.
Yeah.
And when it's decreasing, you're moving left.
So when the graph is increasing, we're moving to the right. And when it's decreasing, we're moving to the left. Yeah, we'll estimate the exact points though. Yeah, so at A, when is our graph increasing?
0 to 12.
Estimate.
0.5, 0.35.
You want to say this is, oh, keep in mind that your interval is, this is 0 and this is 2.
So,
0.7.
You want to say 0.75? Okay. So we're moving to the right. When 0 is less than x is less than 0.75. If we call this the x-axis. there any other time that we're moving to the right? 2 and on. So we'll say when 2 is less than x, or when x is greater than 2. Very good. Those are the times when the graph is increasing. How about when we move to the left? Which is when our graph is decreasing. Uh, 0.75 to 2. So I'll say 0.75 is less than x is less than 2. All right, y'all. Tell me, what's going on at these points, 0.75 and at 2? We're switching direction. So part B, when does the particle reverse direction? Those peaks and valleys. So when x is 0.75 and when x is 2. What questions do we have so far about understanding this position graph?
This is a graph of like distance, right?
Yes, this is a graph of distance. So that means like we move to the right, let's see, like 2.5 units. And then to the left, and we go back to our home base, 2.5, which is 2.5 units back. And then we keep going to the right, seemingly indefinitely. Okay. All right. When does the particle have positive acceleration, and when does it have negative acceleration? What does our position graph look like when we have positive acceleration, when our acceleration is larger than 0? That means it's concave up. So we need to figure out when our graph is concave up.
From 0.75 to greater than 2.
You're close. All right, y'all. Do you agree that we start out concave down? And then at some point we switch to being concave up. And
Oh, that'd be at like 1.25.
yeah, that'll be somewhere halfway between that peak and that valley. So this point, remind me what this point is called when we switch from concave down to concave up?
Inflection.
Inflection point. That's when we switch from being concave down to concave up. Okay. And what did we want to estimate that point to be? Sure. Ish. That's okay. Okay, so mathematically it wouldn't be. Mathematically, what would it be? Halfway between 0.75 and 2, right? So like 0.37. It doesn't matter. But, okay. Positive acceleration means we're concave up or concave down? Up means we're concave up. Yeah, so that's when x is larger than 1.37. And negative acceleration, that's when we're concave down. When are we concave down? I'm going to say between 0 and 1.37 because it doesn't make sense for us to have like a negative time. That's usually what the x-axis means, is like time. But my graph does go to negative time, doesn't it? That's because I forgot to have a domain in Desmos. So we'll say that this doesn't exist. Okay. What questions do we have so far? Okay. The last question is, when is the acceleration 0, correct?
Would it be at 0.75 and 2?
Why?
Because that's when it's like changing direction. So then at that point, you're like stopped. So you wouldn't
Oh.
accelerate.
Maybe they, threw it back U-turn.
I think if you did
We're
one
talking
that
about
fast, there might be a little bit.
But there'd still be a point at your U-turn where you would be parallel, and you have to change direction.
Correct.
We have to say it out loud.
I have a follow-up question for that.
That's definitely the inflection point.
It is at the inflection point, but okay. I want to talk about this though. So, can I just draw this real quick? Goodness gracious. So this looks like a cubic function, right? This is what ours looks like. Does it start? Is it kind of like this? Sketch a derivative graph. When is our derivative 0? When is the slope 0? Ah. Right. At this point and at 2. So that means our derivative graph is going to look something like this. Do you agree? It'll look like a parabola. This is 0.075, or sorry, this is 0.75 and this is at 2. And acceleration is the slope of our velocity, right? So even though this point is where we switch directions, the slope is still slope of this line, and our slope, and we are accelerating, we are slowing down at that point. Kind of make sense?
Sure.
So when our acceleration is 0 is actually at this minimum down here, which was the inflection point right here.
Oh.
Does it make sense? Keep asking questions if this doesn't make sense.
I don't know. Because I also thought it was the inflection point, but I don't know why.
Well, I did tell you on the front page. Maybe that's why.
Oh, maybe.
Those inflection points will get you peaks and valleys on your velocity graph, which is why that's the acceleration is 0 at those points, because they're maxima and minima. So, in conclusion, when is the particle's acceleration 0?
When x equals 1.73.
At the inflection point, when x is 1.37. All right.
37.
At the inflection point at x equals 1.37. Okay. Do we have any other questions at this moment? Do we feel okay about this? Maybe it's challenging but doable. Okay.
Maybe you can watch the wheel.